Okay, here we go. So the last example that we left off on, I had drawn a picture for you. I'll go ahead and redraw.
Where you at? First try. Where you at?
All right, guys. You with me? All right, so I have A and I have B. So these ships, we drew this yesterday. They are 100 kilometers apart. Ship A is sailing south, so it's going at a rate of 35 kilometers per hour. And ship B is sailing north at 25 kilometers per hour. And it says, how fast is the distance between the ships changing at 4 p.m.? Okay, so here's their distance. Okay. So I started out kind of telling you that this is very similar to vectors. So if you guys have had physics before, this will make sense. If you haven't had physics before, I'll try to explain it the best that I can. So basically, did you guys do vector in pre-calc though? You did vectors in pre-calc. So, okay, so basically I'm going downwards. This one's going upwards. Now their distance is here. Does that make sense? Okay, so what I'm going to do is instead of drawing this ship B over there, I'm just going to put it on the end of the other one, right here. Do you guys see how that makes a right triangle for us? Oops, if I wasn't using the eraser. There's my right triangle. Okay, I drew in lots of lines there, so let me get rid of maybe I can get rid of one of these red lines. So let's say I didn't extend. I'm just going to take this one, and I'm going to tack it on the end. So I'm going to go up 25 kilometers per hour. And there's my right triangle. Okay, you'll have that right triangle. I mean, it will just stretch out. It will get longer, right? But the one side of the right triangle is always 100. You guys see? This is 100, because they're always a horizontal distance of 100 kilometers away from each other. All right, so that means that this whole left side, what is that whole rate? Yeah, it's 60 kilometers per hour. So each hour, they are vertically moving away from each other 60 kilometers each hour. Okay, so for my right triangle, I'm going to call this X. No, let's call it Y. I usually try to stick with the vertical ones as Y and the horizontal as X, and then Z. Okay, so I have X squared plus Y squared equals Z squared. And we talked about related rates. So these are all with respect to time. And you should have a clue in this problem because it's saying kilometers per hour. So we need to take the derivative with respect to time. So I'm going to have 2x dx over dt plus 2y dy dt equals 2z dz dt. So we're just taking the derivative implicitly. Anytime I take the derivative of any variable, I put, like if it was x, dx dt, y, dy dt. Make sense? Divide by 2 everywhere. So in these Pythagorean Theorem ones, it's nice because they all cancel. The 2's cancel. All right, so x, what is x at 4 p.m.? It doesn't matter what time it is, I guess. X is what? 100. What's dx dt? 0, right? So I have 100 times 0. It's equal to 0 because it's constant. So we talked about that yesterday too. So if something is not changing at all, the rate of change is 0. Equals y. So what's y at 4 p.m.? 60. That's up for each hour. So what happened in 4 hours? So you started at noon. Okay. So you started at noon, and in 4, it's 2:40. I meant to write 4 hours, like 4 hours. Okay, so they went 60 kilometers for 4 hours. So 60 kilometers per hour, I guess I'll say, for 4 hours. Okay, so I get 240 times 60. Is that positive or negative? It's positive. It's 60 kilometers per hour, and it's positive because their distance is increasing each hour. Okay, so it's confusing for some people because it's like, well, one's going up and one's going down. I don't know. Is it positive? Is it negative? All you're worried about is the distance getting bigger or is it getting smaller? Okay, plus.
Should it be plus instead of equals?
Oh, yeah, thanks. So Cam gets a point. All right, equals z. So z is, how do we find it? Yeah, so I have 240. I have 100. I need to find z. So we do Pythagorean Theorem. So it's 240 squared plus 100 squared equals z squared. You'd end up with 260. Because the reason I know that is because it's a 5, 12, 13. That's another common Pythagorean triple, 5, 12, 13. So see how this was 5 times 20? This was 12 times 20. This would be 13 times 20. So it's 260. So I get 260. And then dz dt, what's that? That's what we're trying to find, right? Okay, solve it out. So 0 goes away. I get 240 times 60. I'm going to divide by 260 to get dz over dt. What'd you say? 55.385. And what's my units? Yeah. So remember I told you yesterday that you usually get a point for just having the correct units on problems like this. So at least do that. And if you need to use this for part B, so if this answer applied in part B, but you couldn't get this answer, put down any number. So you can put down 50 or whatever you think it is. And then you can use that in part B. And as long as your setup's right, you'll get points for your setup in part B as well. All right, makes sense? Okay, so like I said, we're going to skip over this next section. And we're going to do part 3, even more related rates. So we're going to do some trickier ones. All right, so it says sometimes related rates problems can get very tricky. When you first learned related rates, so yesterday, we did not plug in any numbers before taking the derivative. Technically, it is okay to plug in the numbers, though. Some of you guys saw this on your homework yesterday. You guys had example 1 on your homework. So it says 2 sides of a triangle have lengths of 12 meters and 15 meters. Kind of nice I'm doing one of your homework problems for you, huh? The angle between them is increasing at a rate of 2 degrees per minute. How fast is the area of the triangle increasing when the angle between the sides of fixed lengths is 60 degrees? Use the area formula. Area equals 1/2 AB sine of theta, where A and B are fixed side lengths and theta is the angle between them. Okay, so basically you have a length of 12. Oops. And that's a fixed length that's not getting any bigger, and a length of 15. So imagine, I don't know, what's something that hinges like that? So some kind of hinged item, I don't know, where one length is 12, one's 15. Like a compass, I don't know, you can move it back and forth. And the angle between them is theta. Okay, now this line is changing. So the third side of the triangle. So it's getting really big when theta gets really big. It's getting really small when theta gets small. Make sense? Okay, so if you're setting this up, you'd have area equals 1/2 AB sine of theta. So I went to an AP conference last year, and there was one teacher who was very set on never plugging in numbers before you take the derivative, which I understand. Like you don't want to plug in numbers and then take the derivative and get 0, right? But you can actually plug in numbers if it's a constant. So if that number is never changing throughout your problem. So in this case, 12 and 15 are constant lengths. They are not changing at all. So you can plug those in. Now the convenience of this is if I had A equals 1/2 little a b sine of theta, and I took the derivative of those right there, and I assumed they were all variables, they were all changing. If you guys took the derivative, and you might have done this on your homework, you'd have to like break it up into some kind of product. So don't do this. I'm going to show you what you would have had to do. You would have the derivative of the first one, so 1/2, and the derivative of the first one involves the product rule. So 1/2 a times db dt plus dA over dt, b So that's the derivative of the first one times the second one normal plus, do you guys see how this is annoying? The first one normal times the derivative of the second. So cosine theta d theta dt. So this is how you would have had to start this one out. That'd be a lot of plugging in. I mean, it works, but lots of plugging in. Okay, so what I'm telling you is you can ignore that. And if something is constant, you can just plug in. 15 sine theta. So you get A equals 90 sine theta. So dA over dt equals first, so 90, well, the numbers just pull out to the front. So derivative of sine is cosine theta d theta dt over dt. Okay? Is that how you did it on your homework? Yay. All right. So we know that the angle between them is increasing at a rate of 2 degrees per minute. That is d theta over dt. So 2. It says, well, what happens when you end up, when the angle is exactly 60 degrees? So at that particular moment, when it's 60 degrees. You're finding dA over dt. All right, so I would say 99.9% of the time in calculus, I've told you this before, you always use radians. This problem has degrees, so you have to use degrees. So hopefully you did that on your homework. So plug in. So 90. Did you guys get 90?
90, yeah.
I don't know why I plugged that into my calculator. I could easily have done that in my head. So, because it's a nice, it's your unit circle measurement, right? 60 degrees. So your cosine was 1/2. So 1/2 times 2 times 90. Okay, so that is your rate that the angle is increasing, or the area is increasing. What do you think your units would be? Nope. Meters squared per minute, right? Because it's the rate of change of the area. Area is meters squared per unit time. So time is minutes. So meters squared per minute. Good. Okay. A balloon rises at a rate of 3 meters per second from a point on the ground, 30 meters from an observer. So let's put little Allie out here. Was Allie the kite one? I think she was the kite one. So 30 meters. And the balloon is starting on the ground, and it's going up. Kind of looks like a decapitated head, so sorry, Allie. No, you can draw the little string of the balloon. That doesn't look much better. All right. So it's going up at 3 meters per second. Find the rate of change of the angle of elevation of the balloon from the observer. So we're actually going to have it go all the way to Allie's feet. That's not really the angle of elevation, but we'll go with it. It'd really be from her eyes, right? So she's laying on the ground and looking up. All right, so this is your angle theta. So the rate of change of the angle of elevation. So I need something that's relating theta to x and y. So how can I relate theta, x, and y? Good. You guys remember your SOHCAHTOA? So tangent. So it's tangent of theta equals opposite over adjacent, right? So tangent of theta equals opposite was y, adjacent was x. So now we take the derivative. So the derivative of tangent is secant squared. We need to do our derivative drills again, don't we?
Tomorrow.
Tomorrow.
Yeah.
I have it on my to-do list to write it. All right, so then I have y over x. So how can I take the derivative of y over x? What do I need to do? Yeah, quotient rule. So low d high. So low, derivative of high is 1, which is 1 times dy over dx. or dy over dt, right? So dy over dt. Minus high, d low. That's an x. It's kind of a fancy x. All over the square of what's below. So x times dy over dt minus y times dx over dt over x squared. Yes?
I have a general question.
Mhm.
So, when you know
Guys, listen.
dx over dt and dy, it's like when we did just normal derivatives, we never had to do dx over dt.
Okay, your clue comes from the problem that this is a related rates problem because it says 3 meters per second. So when you see meters per second, that's a clue that you're using dt, right? Meters per second. So remember that's a rate, dx over dt is the rate that the x value is changing with relation to time. Now in your normal derivatives, remember we would say like the slope. So slope is the rate of change of y over the rate of change of x, right? Change in y over change in x. So that's why we use dy over dx. Does that make sense?
Yeah.
Okay.
So that's like you're trying to find the rate, but like in normal derivatives, you have to find the rate.
Right, like you're not taking it with respect to a time. So in this case, it's a time. So whenever you see like per second, I would say like red flag. That's your red flag that there's a related rates. So you need to do dt. My Algebra 2 class really likes the red flag. All right, so here we go. So we're going to plug in our values. So x we know is 30. Dy over dt, that's 3, minus y. Now you could find y. Do I need to find y? No. It's all being being multiplied by 0 anyway, right? So 0 all over x squared, which is 30 squared. Now I need secant squared theta. I need to find theta.
Is it 0 because it's not changing?
Yep, dx over dt is a constant 30 meters. So she's not moving like closer to the balloon at all. It's just already there. Yep, you can find theta. How can you find theta? Yeah, so then I guess we do need to find y, don't we? So we do need. So let's see. So we're finding when it's 30 meters. Oh no, we already knew. 30 meters was y. So we have 30 and we have 30. Tangent of theta equals 1. When is tangent equal to 1? 45 degrees, right? So it's at 45 degrees. So you can do 45 degrees or pi over 4. Well, you go back to using pi's. Okay, so you have 30, and you have theta. So that means that the tangent of theta equals 30 over 30. So tangent of theta equals 1. Remember, tangent is sine over cosine. So when are sine and cosine exactly the same thing? Right, at pi over 4. Now there's also another location. What's another location? 5 pi over 4. Why does that not make sense in this problem? It's not, well, it's kind of negative, but you could go negative pi over, or negative, let me think, 3 pi over 4. All right, so, but think about Allie laying here on the ground looking up at this balloon. Why would it not be 5 pi over 4? Which direction would she look at? It'd be backwards, right? So it would be past 90 degrees. So that would really be over here. Okay. Okay, secant of pi over 4. What's secant of pi over 4? Do I need to draw it? 1 over cosine of pi over 4. And cosine of pi over 4 was...
Pi of root 2 over 2, which is 2.
Yeah, I see the wheel spinning. 2 over root 2, which is just...
Root 2 over 2.
See how that becomes 2? It's root 2. Yeah, when you guys first learned square root of 2 over 2, it was really 1 over the square root of 2. That's how you first learned it, 1 over the square root of 2. But we don't like square roots in the denominator, so it's root 2. So I have root 2 squared, so 2, equals 90 over 30 squared, so 900. That's 1/10. So 1/10, and I'm going to multiply, or I'm going to divide my 2 over. So if I have 1/10 and I'm going to divide by 2, what do you get? 1 over 20, right? 1/20. Yeah. Okay, so what are my units? Ooh, I just totally messed this up. It would actually be radians per second because we did it in radians, right? So number 2, a construction worker pulls a 5-meter plank up the side of a building under construction by means of a rope tied to one end of a plank. So I drew this picture for you. Seems kind of complicated. You see the little worker pulling the plank up?
I'd love to see a person.
Yeah, it seems kind of...
Yeah.
I'm going to guess there's probably some kind of pulley that it's not a construction worker, it's some kind of machine that's doing this, but... Okay, so assume the opposite end of the plank follows a path perpendicular to the wall of the building. So as it's going up, this is a perpendicular, like a right triangle here. So as you're pulling it up, you're getting a right triangle like that. You guys see all the different right triangles? Okay, and you're pulling it up at a rate of 0.15 meters per second. So how fast is the end of the plank sliding along the ground, so this part, when it's 2.5 meters from the wall of the building? Okay, do you guys want to try this one first? Think about it. All right, so you're probably going to use Pythagorean Theorem somehow. I would use the triangle right here that I just drew in red. Can you guys see it? It's kind of hard to see. Set it up like that, x and y. Okay. So now we have x squared plus y squared equals z squared. And we take the derivative and divide by 2, so you'd end up with x dx over dt plus y dy over dt equals z dz over dt. So those would all have 2's in front of them, but I've divided by 2. Kind of did 2 steps in one. All right, so we're finding when it's 2.5 meters from the wall. So when x is 2.5, and we're finding how fast the end of the plank slides along. So that's what we don't know. We don't know dx over dt. So slides along the ground. Plus, do we know y? What was it? 4.33? Is it 4.3 repeating?
No, 0.34. 4.330.
Okay. All right, and how did you get that? Pythagorean Theorem, okay. I would probably store that number in your calculator because you don't want to use 4.330 and then in the end round to 3 places. You know, I would use like 5 places if you didn't store it. Does that make sense? So store it in your calculator. Okay, so dy over dt we know is you're pulling it up at a rate of 0.15 meters per second equals 0 because this was constant. It was constant because it's a length of the plank. The plank is not changing size. That would be all kinds of crazy. All right, solve it out. Did you guys solve for dx over dt? What'd you get? Negative 0.259. And it's in meters per second. So do these make sense? Yeah. Let's see if there's a cone one. Oh, yeah, the next one's a cone one. Yay. All right, so you guys had a cone one for your homework. Now what you guys had on your homework was a conical shape that was pointed down. It was a drinking cup or something. I don't know. Okay, and what I told you was if this was 25 and this was 12, you had like the water filling the drinking cup. So here's the water. It's red, kind of gross. Maybe I should use blue. All right, so you have a triangle that is in the same proportion as the bigger triangle. Okay, so basically you have these similar triangles. They have all the same angles. See how you have right angles? Those angles are the same. This one's the same. So it's similar triangles by angle, if you remember that. All right, so whatever your height was, the original height was 25, and the radius was 12 in your homework. This is not for this problem. Are you guys writing this for this problem? All right, and this height and this radius, I told you to do h over 25 equals r over 12 to solve for one of the variables. So if your problem was asking, I think in your homework it was asking for the rate that the depth was changing, so that means you want to solve for dh over dt, right? So you want all of your variables to be with h. We knew nothing about the rate that the r was changing. Now, the nice thing about these is as long as you have this equation, like if you had forgotten to do that and you got halfway through your problem and you hadn't, like, you had dr over dt and dh over dt, you can actually find it from this. Because you could say, okay, well, 1 over 25 dh over dt, so I take the derivative of the left side, equals 1 over 12 dr over dt. So then you could use it from there. Does that make sense?
Yes.
So with these cone problems, you're almost always going to have these similar triangles that you're going to need to use. So when you see a cone, think, oh, I got to replace one of my variables. So, all right, so let's figure this out. So gravel is being dumped from a conveyor belt at a rate of 30 cubic feet per minute. So that's your dv over dt. P.S. I'm a big nerd and I listen to books on tape on my way to school. And my book on tape said something like, she walked around and found the cubic area of the house today. And it made me so mad. So, true story.
You should just read whatever was in the books. The book must have written it that way.
I know. I was mad at the author. It was written in 1940, so maybe they just didn't know about volume in 1940. Pretty sure they did.
The
All right.
cubic area.
Yeah. The heart is a lonely hunter.
Contradiction of
I'm a little bored.
Contradiction of terms.
All right.
Confusion.
Anyway, so dv over dt is 30 cubic feet per minute. So we have this cone. And it says, how fast is the height of the pile increasing when the pile is 10 feet high? Ooh, this is actually not one that you can use because you're not filling, like it's the inverted cones where you would like fill it with water or something. That's when you use your similar triangles. So I just went on that tangent for no reason. So, all right, so let's see. The height is 10 feet. Oh, maybe not. The diameter and height are always equal. So in this one, the diameter and the height are always equal. So that will be 10 at that point as well. So we're going to call that D and this H. So my volume is 1/3 pi r squared H. But it makes it a lot easier to use D in this problem, right? Actually, we're talking about the diameter. So R is D over 2 squared. And then we know D is equal to H. So I have 1/3 pi H over 2 squared times H, because D was equal to H. Simplify. So think of these as all being fractions. Multiply across the top, multiply across the bottom. The denominator is 6. What's the numerator? H to the third, so I'm going to put that to the side, and pi. So I have pi over 6, h to the third. So dv over dt is pi over 6 times 3 h squared dh over dt. And then we can solve it from there.